Hello and welcome back. I'm Babak and this is the third series of lecture on large-scale hydropower. Now we are going to emphasize on the performance characteristic of large-scale hydropower and see their impacts on energy systems. You've seen this equation before, which shows the available energy in water. P equals to rho g h q, the efficiency of the turbine. You could see that the rho and g, they are constants, and then efficiency of the turbine is related to the turbine itself, the design of the turbine, and the manufacturer capabilities of making we could say a high efficiency turbine. For France's turbine nowadays, the efficiency of turbine is around 90 to 93%, so there are very high efficiency turbines available at the market these days. So the only two remaining parameters, they are H, which is the available head, and Q, which is the available flow. And these two parameters play the main role in available power. The flow duration curve, which is for runoff river scheme, you've seen this before in the lectures by Dr. Brijesh. So you already know the definition of reserve flow, firm flow, and design flow. This is mainly for runoff river schemes that they are dependent on the flow. There is no storage or very limited storage of water available for runoff river schemes, as we also discussed in an earlier series of this lecture. But for larger scale, there is always a storage of water available. It's a dam which is built and make a reservoir depending on the topographic and site specification. That reservoir could hold weekly, monthly, or even seasonal fluctuations in incoming water. So if we take a look to this chart here, you could see this shows the reservoir capacity in cubic meter, and you could see along the time, it could be a year or it could be several years, this changes, these available volume of water changes. There are inputs and there are outputs to the reservoir. Inputs to the reservoir, they depends on the hydrological conditions, the upstream conditions, the precipitation, magnitude of flows that come into the reservoir, and also the sedimentation, which in fact reduces the volume of available water. And the output from a reservoir, it could be according to the different needs and demands. For example, irrigation demands, water supply demands, environmental concerns, fisheries demands. The point is that dams are huge and large infrastructures. They are rarely built just only for one purpose, just only as the making a water reservoir for energy productions. So normally they are multi-purposes. So it's at the same time providing storage for electricity, but also water for water supply system or water irrigation systems. So these are multi-purpose dams, we could say. So these different variables and these different parameters, in fact, it necessitates a reservoir management. And then the reservoir management is the key to the availability flow within a period, along a year or along a decade. So all these different inputs and outputs should be considered in reservoir management. And here I could show you schematics of a reservoir, of a dam. So if we look here, this is the dam body itself, and then this is the outlet of the dam that it could go toward the power station plant. So normally this is the top level that a reservoir could have, and if it comes above this one, then water spills over the dam into the downstream. So this is the live storage portion of the dam, and then the dead storage. The dead storage is in fact that part of a dam or elevation of the dam which is considered for sedimentation or for fisheries. This is the minimum level of water that should be there for fisheries. So on top comes the live storage, and then the purpose could be different. It could be a flood control, or it could be a hydroelectric production, or a water supply, irrigation, and so on and so on. So there are different purposes and for different levels. So all these different options comes into the control of a reservoir management. So in fact, what is important is that the available flow in larger scale project, it's not only one queue, it's not only one flow. So the designer should consult with the different parties and consider different scenarios in order to be able to evaluate the available flow. And that flow is normally not constant along the year. It varies also, and then it has its impact on the design of the system, on the selection of the turbine. Talking about the flow rate, then we come to the next parameter, which is the head. The available head, you could see that it's related to the Bernoulli equation, and then the level of the static head on the reservoir side and the available head on the turbine side. There are pressure losses along the system before water reaches to the turbine. In the previous equation that we've seen, that H, in order to calculate the power from hydropower, is in fact related to the head differences between the inlet and the tail level. In order to calculate the available head here, one should calculate the pressure losses in the system. And you've seen it before on the first series of lectures by Brijesh, how to calculate the head losses in your system, which is through the Darcy-Weisbach equation. So you've seen this formula before, and this is applicable to one simple pipe or canal. So it could be, the pressure losses could be calculated. And then you've seen also that there are minor losses that are related to bends or to different valves or contradictions in your system, and each one should be calculated separately. And then this diagram here shows you how the F, or the friction factor, is related to the roughness of your pipe and the Reynolds number, which is on the x-axis. So by having the roughness of the pipe, the diameter of your pipe, you are able to find a proper suitable value here, and then calculating the Reynolds, then you are able to calculate the F. This is some sort of a hand calculation for simple system. In reality, the system is more complex, and as I mentioned to you before, the flow varies along the year, so we do not deal with just one flow and one calculation. Here is an example from a project. So you could see a reservoir here, and then comes the trash rack, inlet gate, intake tower, backup gate, and each one introduces its own minor losses to the system. Then comes a tunnel. The diameter is around 4.35 centimeter, 4 meter 35 centimeter. The length of the tunnel is 42.8 kilometers. So you could see the scale of this project, and it is concrete lined tunnel. Then after converting water, then we have, of course, a bypass system in order to bypass water when there are some incidents or turbines are under maintenance. Then we have a surge shaft, which is in order to eliminate the pressure spikes in the system. We are not going to take a look to this one at this lecture. But the point is that it's a complicated system with bends and butterfly valves, and then finally comes the turbines. So this project has 3 turbine units that you could see here, and water is released to the tail rest. And how this system could be calculated, and of course there are computer model programs in order to model the hydraulics within the system. So what I wanted to highlight here is that, for example, this one shows the results of that program, the available head during the different times. So depending on the, let's say, the reservoir management and then the flows that are released, then the available pressure is also different on turbines. So nowadays, these type of modeling and hydraulic calculations are used for larger scale projects. We will take a look to the calculation part of the larger scale projects in the next lecture in the classroom. We will try to develop the understanding of the hydraulic concept, how to calculate the hydraulic models for large-scale projects through different steps. But then finally, it comes to these sophisticated computer programs to do the modeling. But it doesn't mean that we don't need that basic and fundamental understanding of the system and the hydraulic of the system. We will get that through the calculation part in the classroom. I would also like to point out here about the hydraulic modeling of the other systems rather than the tail race and the turbine itself. So here you could see that there has been some hydraulic modeling regarding the spillway. What happens if there will be an overflow in the dams and water should be released on the downstream? What impact it could have on the downstream side of the dam? Or here you could see the modeling of the tunnels in order to investigate the pressure spikes in the system or the surge pressures in the system. Nowadays, you could see here some other examples here, for example, how making a huge structure on a river could impact the downstream flow regimes, the downstream side of the power plant. But nowadays, a CFD or computational fluid dynamics is very popular in order to make that sort of the hydraulic modelings. Here you could see a very old turbine. It's more than 100 years old in Sweden. It is called a camel type turbine because it's like a back of a camel here. So in fact, it's two turbines that have one common shaft. So you could see the runner blades here, the blades here, and then they are sitting on one common shaft. This shows the turbine, which is decommissioned. The aim of the project here was to model the flow inside a new turbine, because this turbine should be replaced by a new one. So the CFD, or computational fluid dynamics, is a helping tool. So here you could see the different parts of a system, the guide vanes, the runners, and draft tube. They are modeled in computer with the help of the CFD programs here. So you could see the guide vanes, the runner, and the draft tube. And then by implementing these simulation, which are based on finite element methods, in order to solve the mathematical models of the system, one could get an understanding of the different flow parameters inside the turbine. So here you could see, for example, this one shows the velocity contours in different sections of a turbine. So you could see that at the inlet to the guide vane, which is in fact this part, you could see velocity is very low, but then it goes inside the guide vane, the velocity increases, and then velocity is increased, and then it goes into the blade side. So you could see that then the velocity is decreased back again inside the runner, and water, when it is released from the draft tube, then velocity is low again. So by making this sort of modeling, one could have a comprehensive understanding of flow regimes inside a turbine. For example, here we are looking toward the runner blades, and then this one shows that when water comes in, then there are vortices for this specific guide vane opening and these efficiencies. But if we change the guide vane opening, then we get a smooth streamline flows. The point is that now we are able, in order to calculate the best guide vane opening, in order to have the maximum efficiency of the turbine. So these sort of studies are important in making progress, in making a more efficient turbines these days. So I would like to wrap up this session with just highlighting some characteristics of the hydropower. Hydropower is the most mature, reliable, and cost-effective renewable energy technology available. And hydropower is the largest renewable energy source, and it produces around 60% of the world's electricity. In more than 25 countries, hydroelectricity counts for more than 90% of the electricity supply, and it is involved in more than 150 countries in the electricity production. When it comes to the large-scale hydropower plant, then it is associated with the storage of water in reservoirs. And this contributes to the stability of the electrical system, because these systems are connected to the grid, and they provide the flexibility which is deemed to have with an electricity network. And with large power, hydropower plant, in fact, they can store energy over weeks or even over a season, depending on availability of water. So the flexibility of the large-scale hydropower scheme is very important. Thank you for listening to this lecture series. We will wrap up our lecture with the last series about the economics of hydropower and environmental and social aspects.